Okay, first question. It's found that the Geiger-Müller tube registers a count rate even though radioactive sources are not present. So if you have already guessed, this is your background radiation. Okay, so how to explain? This is due to background radiation. It's only one mark, but it might be good to actually explain, give some example of the possible sources of background radiation as well. From just give a few lah, or maybe one from rocks, example, building materials, uh, radon gas in air, etc. Okay, at least give one, right? Okay, next question. It shows an experiment to investigate the deflection of beta particles from sample Y. And we have this source coming through an aluminum sheet with a hole, and it passes through this horseshoe magnet. And the Geiger-Müller tube seems to be to the left, to below. We read is at the bottom. So the Geiger-Müller tube is actually at the bottom. That means the path that is taken by the electron, the beta particles, which has the same charge as the electrons, is downwards. That means it must be going through the hole, and then there is a deflection downwards because of the magnetic field. Okay. Now, so what is the nature of beta particles? Let's answer that first. Uh, okay. Okay, let's do it. Beta particles are high energy, negatively charged electrons. Okay, very full answer. We describe all parts of it. Negatively charged, high energy, at the same time saying that it's an electron. Okay, that's good enough. Half life of the beta particles that was used is 10 days. Maybe I should change to blue. Okay, this one also change to blue. Half life of the beta particles was used is 10 days. Determine the fraction of they will remain radioactive after 40 days. Uh, so there is 4 life cycle. So 4 half cycle. 4 half cycle. So fraction that will be left. So one after one half cycle become half. After another half cycle become 1/4. So this is the first, second, third half life. Then it becomes 1/8. Then another half life, it becomes 1/16. So the answer is 1/16. Just keep it simple maths. Don't need to give some very complicated formula. Okay, so the answer is 1/16. Suggest the purpose of the aluminum sheet in this experiment and minimum thickness for the sheet. Okay, aluminum sheet can block alpha particles, but it cannot block beta. Oh, it can, but it must be thick enough. It can block alpha definitely, but it can also block beta, assuming that it is thick enough. So, what is the thickness needed? A few mm will do. Okay, so number one, this one. Wait, let me copy here. The purpose is to direct direct the beta particles through the magnet. Okay, I think that's a straightforward answer lah. Copy, paste. Okay, what's the minimum thickness needed? I would think at least a few mm. Maybe we can just play around and say it's 3 mm. That's good enough. If you're very kiasu, you can say 5. Okay, but this should be enough. 3 mm of aluminium. State the polarity. Okay, this part we need to do the Fleming left hand rule if you still remember in the previous chapter. Okay, so now just going, I can't show my hand here, so I'm just going to draw here to see where all the directions are. Now the beta particles is negatively charged, so it's opposite, okay, to the direction of the current. So the current should be in this direction. Okay, we do not know the magnetic field, so we'll skip the magnetic field for now. But we do know that there is a force directed downward that deflect the beta particle downward. So the force should be downwards. So this is your F, that's your current. So in this case, use your Fleming left hand rule. You will see that your magnetic field is directed into the pitch. You see that the magnetic field is directed into the pitch. So in this case, then your pole P should be your south pole. So that means your P is south, or just right there, south pole. Magnet is replaced by two metal plates and a power source. Describe and explain how the experiment can be modified so that the Geiger-Miller tube can detect the deflector beam at the same position. So now what we are doing is that we are actually replacing the magnetic field away with a electric field. So how can we actually force or make the beta particles follow the same path as before? That means we must direct it downwards. So direct, and it's negatively charged. So if we have a plate on above, which is negative, we will repel it downwards, and if it's positive below, so that's what we will do. Okay, that's what we will do. I will place the plates horizontally. Place the plate horizontally with the top plates. The top plate being sorry, we need it to be positive and negative. We need it to be negative, being negatively charged, and the bottom plate being positively charged. Of course, you can also say the top plate is connected to a negative terminal of the power source, and the bottom plate is connected to the positive terminal of power source. They will give the same result. But otherwise, that should give you the 2 marks to say that they are being placed horizontally. Okay, at the same time, oh, maybe I should say between the some where exactly is the position. I must say between the source and the between the aluminium sheet and the Geiger-Miller tube. Okay, let's just add that in horizontally between the the aluminium sheet and the Geiger Mueller tube. Okay, this should be perfect. 2 marks. Okay, the source is now replaced by alpha source, and the manic is placed back in between the aluminum sheet and the Geiger Mueller tube. So we replace back the manic, but we now have an alpha source. What is going to happen? Let's look at it again. Now we have our manic. Alpha source is actually positively charged, so it should go upward and not downward. Okay, if I were to draw, because it's positively charged, you can use your Fleming left hand rule now that you know the poles of the magnet. You will see that it should be something like this. So that means the Geiger-Miller tube being below will not be able to detect the alpha particles at all. So how would that affect the reading? The reading will drop drastically, but it will not reach zero because there is still background radiation. Will drop drastically until the background radiation level. Uh, State and explain. Okay, I just stated, but I did not explain yet. So that's my second mark. Okay, the beam of alpha particles will be deflected upwards and away from the GM tube. Thus, it cannot be read on the registered. Yeah, it cannot be registered on the counter. Okay, then that's cover my 2 marks. Okay, next question. Radioactive source stored in a safe manner with a hinge, blah blah. So which type of radiation produce the strongest ionizing effect? Recall from your alpha, beta, gamma. Strongest ionizing effect belongs to alpha, but at the same time, it has the lowest penetration power. Next one, which is deflected most? Which is deflected most? Now, both alpha and beta can be deflected, but beta is deflected more because it has a smaller mass. That's why it's more affected by it. It's deflected most. Beta, its mass is much smaller. Okay, sorry about this. Basically, what it's saying here is 10 cm away is without radioactive source is reading 200. When the source is being placed 10 cm from the GM tube, is reading 800. And if a paper is placed between them, it is now reading 800 units. It is now reading 800 units, which means to say the paper is not able to block anything at all. Okay, and if the paper is removed and replaced with a 5 mm metal plate, the counter now reads 600. So what does this tell us? Okay, it tells us a lot of things actually. We're just going to analyze it bit by bit here. Okay, but I think the question, take note, don't explain extra stuff. How to show that it emit only beta and gamma, but not alpha? Okay, the background radiation is 200. So first thing, it does not have alpha because once you block with paper, it is still reading 800. So we can certify that there is no alpha because paper will block all the alpha away. Okay, so first, uh, the reading with or without the paper is the same at 200. Oh no, 800. This shows that alpha particles are not present. Okay, since it cannot pass through paper. Okay, since it cannot pass through paper, if it's present, it should have been reduced. Okay, since there's no reduction, means there's nothing, there's no alpha at all. Second, um, when a piece of metal, this one can block beta, is placed, the reading drop by 200. This shows the presence of beta it shows the presence of beta particles as it can be blocked by a few of aluminium. Okay, lastly sounds a bit strange. Next third lah. Okay, the count rate of 600 indicates presence of gamma as it can pass through. If it is not present, okay, the rate should fall to 200, which is the background radiation rate. Okay, the counter, no, the count rate should fall to 200. I just want to bracket that is background radiation. Okay, I'm done here. Okay, so this should give you 3 marks. Explain why it can protect completely. That's easy. Because it's made of lead, or it's made of a few cm thick of metal. Okay, the box is made of lead, which can block. Actually, absorb. Okay, lah, up to you when you write block or absorb. ABSORB or absorb alpha and beta radiation. Totally. But can only block gamma partially. Okay, that's about the answer. The next question, figure 10.1. Give detail of some radioactive isotope. What is meant by a beta particles? So once again, when we come to this question, just throw in what I throw in earlier. Okay. Remember what I wrote just now? I wrote high energy is negative and it's an electron, right? Negatively charged electron. Say so I'm just going to take away the S. Okay, next take the isotope with the strongest penetrating power. So now we know that alpha has the highest penetrating power. Wrong. Highest ionizing power, but it has the lowest penetrating power. So the highest penetrating power should be gamma. But there's two of them. There's two of them. So what we're going to do? They say state the isotope. Um, I would say either one. I don't think the teacher really planned this properly. I think you state either one, you should get it correct as long as it's gamma. So cobalt 60 or tactinium 99, both you should get a marks. Cobalt 60 or technetium 99. So that's the answer. Oh, sorry, that's my answer. This one, this is for the next one. Okay, so I'm going to use my pen. Uh, 16 times more. So 16 times more means it has dropped by 1 over 16. Or the amount of tissue of carbon 14 found is 16. You drop to 8 times, drop to 4, drop to 2, drop to 1. So 1 half life, 2 half life, 3 half life, 4 half life. So how much is 1 half life of a carbon 14? It is 5,600 years. So 4 times 5,600 years. And this will give me 22400 years. Okay, right here as well. Okay, let me just read back. No wonder it's 2 marks. I miss out one part. How it should be stored safely. Okay, if you are talking about gamma, it should be stored in a lead box. Okay, should be stored in a lead box. Okay, radioactive sources are used to detect leaks. Some liquid leaks. State the most suitable isotope. What should we use? We should use gamma. Okay, why? Because gamma uh, need to pass through the soil and everything because it needs to be detected above ground. So you need to pass through the pipe. No, you shouldn't pass through a pipe. You should pass through the soil. You should pass through the grass. You should pass through a lot of things. Alpha will definitely fail. Beta most likely will fail. because I don't think it can pass through such a thick layer of soil. It can pass through a few cm of metal, but I don't. It can be blocked by a few cm of metal, but I don't think it can pass through such a thick layer. So we will still use gamma, and more importantly is the half life. I need the half life to be short, so that it does not stay underground. So I will be using technetium 99, 6 hours. That's the shortest I can find. So technetium, or how to spell it? Netium. Dash 99. State the most. They never ask me for a reason, so I'm not going to give the reason. The reason will be here. Explain why the half-life of the isotope you have chosen and the radiation it emits are suitable. Okay. Uh, it is chosen because it is chosen as it emits gamma radiation, which which is needed to pass through the layers of soil to be detected above ground. The half-life is only 6 hours, and that will ensure that the radioactive source will not stay underground for a long time. That's because after 6 hours only half will be left. So after maybe like 4 or 5 half life, it will be almost completely gone. So that's why I would say I want to choose as short a half life as possible. That's why you will say we will not stay underground for a long time. Okay, next question. Another source of background radiation, except cosmic ray. Cosmic ray, of course, is one because coming out from the outer space. Another source. Can you remember we wrote a lot, so we can name a lot actually. We can say rocks, building materials, radon gas from the air or atmosphere. Okay, limited three. Next, state one effect of background radiation. Cancer, ionization. A lot of answers. A lot of answers. Ionization or affect count rate of GM tube. Of course, you can also say it cause cancer, but again, that's a bit hard to prove at this kind of low level. Yeah, affect count rate of GM tube. That's good enough. This I give two already. They only ask for one. Explain how the Earth atmosphere reduces the number of alpha particles that reach the surface. Okay, we're going to do this is all right. Alpha particles have low penetration power or low penetrating power. Sorry, power, and most of it will be absorbed and will be absorbed by the atmosphere. Okay, I think that's mostly what it wants. What is the time taken for, or what is half life? Again, it is the time taken for half the mass of a radioactive substance to decay. It's half the mass. And then once again, we have to calculate half life. Okay, let's calculate how many cycle has gone by from 200,000 to 25. So we start with 200,000 and then we drop to 25 because the living specimen is 200,000 and the specimen of wood is 25. So we want to see how many half life have we actually gone through. So this is one half life, this two half life, and then we reach here three half life. So we have gone through three half life. So three times what is the half life of carbon 14? In this case, they say it's 5,700, and we'll get 17100 years. Remember to write in the unit to the years. Okay, or not, you get deducted marks. Okay, let's continue. Carbon 14 is one of the isotope of carbon. What does describe how it differs? So basically, it's just asking you what is isotope indirectly. So you can say the nucleus of carbon 14 has the same number of proton but different number. But you want to add value, you can say but two more because it has two more, but two more neutron compared to nucleus of carbon 12. No, carbon 12. Okay, next question. Atoms contain proton, neutron, and electron. Identify the particles that has a much smaller mass. Okay, I hope you remember. It's your electron. And are lost from the nucleus during alpha particles emission. What is lost? What is so? You might ask yourself, what is the alpha? What is inside the alpha? You have two proton and you have two neutron. So basically, two protons and two neutron. Give them the number as well. Doesn't take much effort. Okay, and it enters a magnetic field. So what is it going to be? This is gamma. So is it affected by magnetic field? It's not affected by magnetic field. So it should go straight. Some atoms that undergo radioactive decay has half-life of 6 hours. The count rate is initially 838. Radiation near the sample. Okay, again, what is background radiation? See how the question keep repeating itself in a way or another. Also, it helps to actually know what is background radiation. So what is meant by background radiation? Radioactive radiation. Radioactive radiation sounds a bit strange. Nuclear radiation. Okay. Radio. Oh, okay. It is radiation due to natural sources, such as radon gas, in the air, or rocks and building materials. The equipment is left undisturbed for 12 hours. How many half-life has it gone through? The half-life is 6 hours, so we have gone through 2 half-life. So from 838, we have to minus away first for the count rate. So 838 minus the 18, that will give me 820 pounds per minute. Okay, this is the initial count, and I gone through 2 half-life. So 820 divide by 2 times. Of course, you can also make it look very nice. You say times half 2 times. Times half times half. And use your calculator, you should get 205. Okay, so your count rate is 205 counts per minute. Take note, every time they never give you the unit in the answer line, please write your own. Do not be so arrogant and then they minus your marks unnecessary.